Hello everybody, welcome to, very exciting, the first video in our physics class. Bear with me with this, it's all very new, but let's dive straight in. So today we're talking about energy. Now when you think of how we use the word energy in everyday life, you might say, don't give the kid too much candy before they go to bed, they'll have too much energy. You might think about the power supply, the power grid supplying energy. Those are good examples. Well, in physics, energy is defined as the ability to do work. Put that right there, very snazzy. Now that's great, except what do we mean by work? Well, there's two kinds of work that we can do. The first is mechanical work, and this would be moving something. This would be work done against a force, moving something a certain distance against a force. So you could think of lifting something up, pushing something across the floor. Those are good examples of mechanical work. In the slides today, the example I gave was an elevator car lifting up against the force of gravity in the elevator shaft. The other kind of work is work done heating. So that could be an oven, that could be a fireplace heating up the room. So those are our two kinds of work. And if we have energy, no matter what form it is, it has the ability to do one or both of those. Now energy is also conserved. We've seen that before with conservation of momentum. Lots of things are conserved in the physical world, or energy is one of them. So what does that mean? Well, it means that energy cannot be created or destroyed. There's just a certain amount of energy, and it can transform from one type to another, but we always have the same amount when we start and when we finish, just like we saw with conservation of momentum. Type that in here. And we're going to look at a couple of examples of this, and these will help with the homework too. So one way you can think of it is, a good analogy is money, dollars. You can give somebody money, you can spend money, they can then in turn spend it on other things, but the money is always there. It might get transferred from person to person, that's kind of like transforming from one form to another, but the total amount of money stays the same. So the examples that we're going to look at, first of all, for conservation of energy, are a simple pendulum. So let's have a go at this. Here we go. So here's our pendulum, the ball there on the end of a string, and it can swing up this way and swing down again. So it swings up, swings down, and of course it can swing over to the other side. Okay, excuse the drawing, but that's hopefully clear enough. Now there's two kinds of energy that we're going to look at here. One is potential energy, which we're going to write as PE for potential energy, and this is short for gravitational potential energy, and that's equal to mass times the strength of gravity times the change in height. In the textbook they just put h for height. I like to put delta height to show that it's the change in height. A lot of textbooks do that too. Now if we look at this pendulum, when it's up in the highest position right here, it's lifted up from this base level here. We've lifted it up to get it started, and then we could let go and it would swing. By lifting it up, we've given it some more potential energy. How much? Well, we could use the formula mg delta h to calculate that, and we'll do that in a second. When the pendulum swings down, when it gets to this central position right here, that potential energy has been transferred into movement energy. Movement energy we call kinetic energy. I'll just write Ke, and the formula for that, which you'll need also for the homework, is half times m, the mass, times velocity or speed squared. When it's in the central position right here, all of that potential energy that it had when it was raised up has now transferred to kinetic energy. When it's in the lowest position, all of the energy that the pendulum has is kinetic energy. So I'm going to write that there. When it gets to the top, it swings over to this left side here. When it gets to the highest point, all of that kinetic energy then transfers back to potential energy. And it just swings back and forth, back and forth. When it's halfway up, like I said, let's say the pendulum is here, and it's exactly halfway up, then half the energy would be potential energy, half the energy would be kinetic energy. So it just swings back and forth, gradually transferring from one to the other. So let me make a new slide because I've run out of space. Okay, here's our pendulum again. So now let's use those formulas. So for potential energy, we said it was the mass times the strength of gravity times the change in height. So if we say that the height that we raise it up is 50 centimeters, that would be 0.5 meters. Excuse the writing, hopefully I can get that decimal point in there. There we go. 0.5 meters. Let's say that the mass of the pendulum, the bob, is equal to 100 grams, so that would be 0.1 kilograms. Struggling with these decimal points here. There we go, that'll work. And of course the strength of gravity here on Earth we can approximate to 10 newtons per kilogram. Alright, so we've just plugged these numbers into our formula. So we can do that over here. So we've got the mass, 0.1 kilograms. We've got the strength of gravity. And then we've got the height, which we said was 0.5 meters. I'm going to leave the units out because I've run out of space. Apologies for that. Hopefully you can follow where these numbers are coming from. So you could, we can see that that was going to be 10 times 0.1, which is 1 times 0.5. I need to get the hang of this stylus. Not quite Khan Academy yet, is it? We'll get there. And eventually that is equal to 0.5 joules, and that's the unit for energy. Joules, named after Joule, a French physicist who did a lot of work in the Industrial Revolution on understanding energy. Okay, so that's one example. The next example we're going to look at, also helpful for the homework, is a roller coaster. So here we have a roller coaster. There's the track. Here is the car. And similar to the pendulum, when it's high up, so that's its highest point, the only energy it has, this is right before it's moving, is gravitational potential energy, which again I'll represent with PE. And then it flies down the slope, really lots of fun, and by the time it gets to the bottom, all of that energy now, because it's at its lowest point, all of that gravitational potential energy is transferred to kinetic energy. And then it starts to go up another slope, and by the time it gets up to here, not all of it, but a lot of that kinetic energy is now transferred to potential energy. So here we've got potential energy. It's still moving, so we've got both. And then it slides down again and loses some potential energy as that is transferred to kinetic energy. So in this example, we're now going to calculate the kinetic energy. So if we say that we were going to calculate the kinetic energy at the bottom of the track, where all that potential energy is turned into kinetic energy, we would use this formula. So kinetic energy is equal to half times the mass times the velocity squared. So it's a little bit different, this formula, because it has the half in and it has the velocity squared, but it's pretty straightforward. Let's say that the mass of this car on this roller coaster track is 500 kilograms. And let's say that it's moving at a velocity of 30 meters per second. So we now substitute those into our formula. So we've got a half, that's just always there, that half. Doesn't have any units, just a number. And then we've got the mass, so that's going to be 500 kilograms. Again, I'm leaving the units out just to give myself more space. And then we've got 30 meters per second as the velocity, and that has to be squared. So that's just 30 times 30. So we can now simplify this. We've got half times 500 is 250 times 30 squared, which is 900. So again, that's just 30 times 30 gives you 900. And you put that in your calculator and you get 225,000 joules. Lots of energy. So if somebody asked you, well, how much gravitational potential energy did the roller coaster car have when it was at the top, when it was over here, due to conservation of energy, because we've calculated the kinetic energy at the bottom of the slope, that would tell us that the potential energy at the beginning was the same value, because energy is conserved. Alright, thank you.